Good morning. Let's stream. So today I'm going to try and get two things done. I'm going to try and automatically set the noise bound, and I'm going to get SPIRiT, regularization, and the non-rectangular support both up and running. And I'm basically going to stream until those things happen, or the lights turn off, or somebody bothers me, or rather interrupts me. So yesterday at the end of this little stream that we had in the evening, I think we realized, and I realized that we're not going to be able to solve this problem that I've been working on with Vista. And that makes sense because the SPIRiT regularization function itself doesn't have a simple proximal operator. We've got to modify it to be able to use, to be able to give it a simple proximal operator that can be used with PDHG. We've got to define this A linear transformation, and then with that linear transformation, then we have a simple proximal operator for the function G that's composed with the linear transformation. So that's what we're going to do today. That's how we're going to start, I mean. Here we are. Okay, so what does that mean? That means that F is no longer going to be empty. So where does F get defined? Okay, F hasn't been empty. Fine. I don't think we're going to need F grad. Instead, we're going to use the proximal operator of F. Nope, we're not even going to use that. We're not even going to do that. We're not even doing that. So I guess based on each of these things, we're going to have to define these functions and choose how to minimize them. So here, F is going to be greater than 0, and G is going to be greater than 0. Okay, I see. So, yep, F we're going to have to set equal to empty. You don't have to. What's going on? Okay. Let's see if we can figure this out. Come up with a game plan here that makes sense more than just the next turn. We solve this with LSQR. We solve this with LSQR. We solve this with Vista. Then we want to add this constraint in addition to those. So this constraint in addition for each of those problems above. Okay, so the most obvious difference is gamma. If gamma is supplied, then we do stuff. So what's the issue? So for here, the objective function, is equivalent to 0.5 times this term squared, and that's differentiable, and we can solve it with LSQR. Same here. Here, the objective function, is differentiable, and the constraint has a simple proximal operator, I think. Yes, it does. And so this can be solved with Vista. Okay. But when we add in this constraint does not have a simple proximal operator. And that's the issue. So once we add in gamma, we have to take advantage of PDHG. Now I've come to learn that there's an algorithm called PD30, which can minimize f of x plus g of ax, where f is differentiable and g has a simple proximal operator. So that could be used here, but I don't think it would be as efficient as PDHG when f has a simple proximal operator, which our f does, f being the objective function. So I think we're going to use PDHD instead. Plus PDHD is a line search, and I don't know that PD30 does. Hopefully it does, and I'd like to learn more about PD30, but today we're going to be using PDHD. Okay. So if gamma is not supplied, then F equals this. If gamma is supplied, then F is empty. Why did I choose the noise bound here? I see. So how does this code work? We start out by creating all the functions. Then we do checks. These are all the linear transformations, the functions that apply the linear transformations and their adjoints. Then we do checks. Then we set up the functions for our optimization. So let's write that down. Create linear transformations and their adjoints. Here's two checks. Check the linear transformation adjoints. I don't know that we need these comments, but they just kind of help me break up the code, and hopefully we can fold some stuff now. Ooh. MATLAB won't let me fold one of these things. I really like them. Okay, and then here, create the functions for the optimization algorithms. Okay. So we're starting out by creating the G's when G's are necessary. We do G support, G SPIRiT reg, and now we're on to F. Okay, so this, as we discussed yesterday, is just semi-appropriate for right now, but it's not appropriate in general. I think apply ADC changes based on whether, apply ADC changes based on whether we have a noise bound for the region outside the support or not. So it's either MFS or MFSBT. Okay. That seems reasonable. So here's what I'm going to do. After G is created, no. Okay, if the support is greater than 0, oh no. If we're doing spirit regularization, then F is equal to that. Yes. What's prox F defined? I've killed prox F. Okay. Okay. Now we've got F, prox F, G, and prox G. So F and prox F are both empty. We're not going to use those, but okay, so now this is making me happier. Okay. This is LSQR, right? Here we're doing LSQR. Here we're doing FISTA. Here we're doing LSQR. No, here we're doing what? I don't know yet. This is LSQR. So F is equal to, and G is equal to that, and prox F is equal to that. So if the null of F and the null of G are both zero, if they're both 0, then we just do and so for this code, it looks like I'm going to assume for this code, we will assume the following. F is a differentiable function. G has a simple proximal operator. Yeah, okay. Where does noise bound get used? Noise bound gets used by prox G support. We don't need this anymore. So for this one, now we're going to use PDHG. And so since we're assuming that f is a proximal, is differentiable, like normally we could let f be this function, the data constraint. And maybe that's the right way to go. And then I could just have flags that say like, do PDHG, do LSQR, whatever. That might be best. But then that gets rid of, alternatively, I could just make A different and then have G return everything. Okay, check me out here. So f is defined here, but prox f will be defined here, but not here. And now I can distinguish between the two. I could always use flags. That would not be an issue. I forgot to tell my amazing audience that I'm streaming. Oh, looks, Jeff Hunt is having a show. Okay. Okay, so now we need the prox f. And I think I have the prox of L2 square, which is that. See if we can do that. Prox f equals at in prox L2 square. V is going to be its input, which is in. Then we have TBA in T B apply A B C. Does that work? AGC is already a function handle. Seems like that should work. It, of course, is not type frame, so we don't need to worry about that to do right now today. think it should be something like this. If nominal gamma is greater than 0, what does G support H? Okay, we've already got function handles. And by default, they're empty. So we don't need numL gamma now. So it's like, if numL G support H is greater than 0, here we're doing proximal gradient. And I think for each function so far, F is this. For LSQR, O. No, I was wrong. See, here we're creating G support H. We're creating G because the support's greater than 0, but, well, I've changed things, so maybe there was like a noise bound thing here before. This is all messed up. How do I know that I want to do LSQR or rather, how do I know I want to do FISTA instead of LSQR? If I want to do FISTA, it's because G support H is greater than 0. If either of these are true, then we're at least doing FISTA, we might be doing PDHG. If numL G SPIRiT reg H is greater than 0, now we're doing PDHG. If they're both greater than 0, then we're doing PDHG. If we're not doing SPIRiT reg and we are doing the support thing, then we're doing FISTA. So I don't have to set those because by default they're empty. Here, we're doing this. I feel like I have a cardinal map in my head, trying to find when to do things and come up with, conditions that would allow me to define one thing instead of define them in each case. Maybe it's better just to define them in each case. I don't know. Okay. Now here we have to do PDHG, I think, because G does not have a simple proximal. Well, G of AX does not have a simple proximal operator. G has a simple proximal operator. So now we need to define prox of F, which I did at some point. Where is it? Okay, A is equal to that as well. Maybe I should have an apply A. Do I already have that? No. Here, apply A is the identity. Don't want to have to do that. So I'm just going to modify PDHG so that if apply A is empty, it doesn't do anything. It doesn't get called. It's assumed to, if it's empty, it's assumed to be the identity. So I think apply A is always that. A is, okay, create F, G, and A so that minimization of F of X plus G of AX. So that optimizing so here F is differentiable. This one minimizes Vista. So if num-L prox G is greater than 0 and num-L of prox F is greater than 0, let's do that in order that we have the rest of the code in, then use PDHG. Else if num-L prox F is, prox G is greater than 0, num-L prox F is equal to 0, and num-L of prox G is greater than 0, use Vista. Else if num-L of prox F is greater than 0 and num-L of prox G is equal to 0, I don't think we have this. Error, cannot set prox F without setting prox G, else use LSQR. Here, both proximal operators are 0. Let's take LSQR and put it here. Where'd it go? Beast of a code, man. Beast of a code. I think this is going to come after. If we supply the support, and do not supply the noise bound, then we're always going to have this PT in the data consistency term, whether that term is incorporated into the optimization as a proximal operator or not. Okay. Perform the optimization. Okay, so now, okay, and then we'll put down here support functions. So what do we got going on now? Now our code is broken up into 4 different parts. I wish I could just fold away one of these, I forget what they're called, like sections or something, but it doesn't seem to be in the cards. Create linear transformations in their adjoints. Check the linear transformation adjoints. I guess I'll just say check the adjoints. Create functions for the optimization algorithms, F and G. And then here, perform the optimization. Don't have to set this if it's empty because it's already set up here. We'll only set things that we're changing away from empty. Here we're going to need apply A. Right? Apply A is equal to at in T. So the first part of apply A is going to be what the support, what this term involving the support requires. So that's just the number of elements in the support. P, let's say complement transpose. It's actually the number of elements outside the support. Or am I wrong? Okay, so no. Okay. X is the full image, and then PC takes out only the region outside the support. Okay. In from 1 to n support. And this is apply fs into n support plus 1 to n support plus nk data. Nope, not true. An image. The output of this is nk data, which is why n in spirit reg is nk data. Ooh, I just got a citation in one of my publications. Excellent. When I was a grad student, that used to excite me so much. I still get excited, but now I'm going for like a paper with 1,000 citations. That would make me excited again, like it did in grad school. Okay, we have A here. Here, G is just G support H, so A is the identity. No need to worry about it. Here, A needs to be created. Apply A is equal to at. Apply A doesn't take a parameter T. The answer is it's apply NF, FS. I think because we do have prox G. Wait. Is this the one where prox F and prox G are defined? So this is going to do PDHG. So I need to apply A. Unless A is the identity, which it is not. Because here F is this function and G is G spirit reg. G spirit reg gets applied to FSX. Or W minus M FSX. Whoa, I totally messed that up. Oh, shoot. Shoot. Apply A needs an operation for its adjoint. And I can't do that easily in line. And I can't define a function within an if statement, because MATLAB doesn't allow that. So this is going to have to be cat I with W minus I fs. No. Yep. That's what's going to have to be. Well, in that case, I don't. So now I have to define concat I with W minus I fs. Is that actually right? Why is this an error? I think that's right. Let's add that into do checks. We're going to replace W minus I with W minus IFS. It's going to be S image. Okay, so in is size as image, and we're doing the no transpose. No transp. that fix it? Nope. This is not a column vector. W minus IFSN is equal to so we're going to need some reshapes, I think. No, this is silly. What's 65536 times 2? Because this is NK data. Incompatible sizes. Shape this image. FSTWMIT in 2 is equal to SK data. Shape this image. See if that works. Well, that worked. That worked. Now let's just see if do checks passes. I clearly think stuff is right when it's totally wrong. It's okay. We let the computer help us figure that out. This now passes. Okay, so in this case then, which one was it? This one. Is this where we go? Okay. Wait, what? Right, okay. We've set things up. Unrecognized optimization algorithm. Okay, we're just using Vista here. Fine. Hmm? Hmm. We're creating F, A, and G. Oh, that's why it was taking so long to get here, because of the power iteration. Whoa! What? PDHG, not GH. All right. NPix. Where's NPix? So call that NImage. Is there NPix anywhere else? Gammas. Apply A, unrecognized function or variable. Prox L2 squared. Why is that? So SPIRiT lets me put, or I mean, MATLAB lets me put a breakpoint. And what does that do? Pause execution at line 334? Let's try that. Is this me defining the function in anonymous function? Okay. Ah! Okay. apply A. DC is a function handle, which is apply MFS. So what's the issue? If I go prox L2 squared, well, here we're just defining a function. Ooh, this is doing CGS? That's not at all what I want. Undefined function or variable, apply A. Okay, so this does not have a simple proximal operator. What on earth was I thinking? We have it here too. Man, if I thought more clearly, it would save so much time. We've been at this an hour already. What are you going to do? This is weird. This should either be like, this should be if numl support greater than 0, else, and this should be PT. One less bug to go. Infinity left. If you had this, you would just do proximal descent, but we never have this. Right. Not proximal descent, but just proximal iteration. Here, by calling this apply ADC instead of just apply A, we're assuming something about FISTA, that it's minimizing, And by using power iteration and calling this the Lipschitz constant, we're assuming FISTA is minimizing F, where F is the L2 norm of AX minus B squared. It's fine. Okay. Back up here. Now I need G support DC. Not G support DC, just GDC. Data. This is just L is equal to norm squared of X minus B. Prox GDC is equal to at prox L2 squared prox at in L2 squared in TB. Since there's no A, prox L2 squared uses this, which is indeed a very simple proximal operator. What I'm trying to do is avoid using a numerical algorithm to solve the proximal operator, which can be done, but makes everything slow. Okay, so now coming back to these definitions. So now we have GDC and we have prox GDC. That's already a function handle, so we don't need to make it an H. I guess I could just call it H, prox GDC. Okay. Now we're back with this mess. So now we want ADC. Just guess I'll call it ADC. change check. I don't want to do that. Okay. Where is this thing? ADCH in, I guess T is what we're calling it now. H in. It's the Hermitian adjoint, not the transpose. Apply a DC in 1, 2, NB. Do we have an NB? Where's B? NB equals num LB. So num samples. NB an image plus 1. Reshape it here. Oh boy. Let's see where it crashes. Unrecognized function or variable. We actually need apply A. I guess, yes, it makes things simpler. Okay. I see, I did it over there, so I'll have to do it once. Okay. Apply FS. That'll work. No, it won't. What? Oh, we have FS twice. ADC is applying FS. W minus I applies FS. Shoot, that's an inefficiency. All Yeah, so then it's this thing. Shoot, 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 shoot. Pretty complicated. All right. Here we go. If NumL, do we define MFSPT all the time? If we are using MFSPT, then FS is embedded in things. Okay. I'm doing a lot of coding to use apply P inside the data consistency term. And that probably isn't a good idea. Nevertheless, we're going to do it. Okay, so in that case, we're just going to bite the bullet, and we'll take advantage. We'll just have to. We're going to just do this inefficiency. We're going to call fs twice, which is painful. Let's deal with that some other day, shall we? Now that should work, right? Good. Now here. Okay. Nice. So here we're doing, this should also use Vista. Right, because now, well, no, it shouldn't. Because we've got this apply A, but why isn't that W minus M? W minus IFS, I think it should be. For G spirit reg. H. Right? G spirit reg H is G spirit reg, just as a Frobenius norm. So it's meant to be W minus IFS. Okay, so that's what that should be. Okay, so now the issue is we're not defining prox G. prox f, I mean. F doesn't exist, right? It's just empty now. So how do I know to use PDHG here? Going to the flags. We also use PDHG here. Here we use Vista. Use PDHG, use Vista, use LSQR. Now I think that, by the way, I think we've changed A, haven't we? So we should recalculate the norm of A. What is the norm of A? 790? Okay. I suspect PDHG is going to fail because I think it assumes that F and prox F are both defined. Let's find out. Must supply F, right? So now I'm going to assume that if you don't pass in F, it's the identity. Or if F is empty. Sorry, not the identity, but it returns 0. Okay. Is it really just used to calculate the objective values? If it is, that's very nice, because then we're only going to do this if statement when we're outputting objective values, which we only do when we're debugging. I guess I could just supply the 0 function. Where's prox F? But what about prox F? So this one we'll do all the time. What happens to temp? So we have to copy here. But I could just call this X and then call that X, which I'm sure I didn't do because I wanted to see temp and X while debugging. But now I don't have to. I'm not debugging. Probably just added in a bug, so I'll have to debug and I'll have to undo that, but one step at a time, man. One step at a time. I don't know what that's about. Let's get rid of that. What was the last error? Incompatible sizes. X has size 256 by 256. Apply A is this. Now we're going to go into G. First thing to be called is GDC. NDC, what is that? That should just be NB. Okay. Oh, almost ran. Almost ran. Too many input arguments, huh? Let's see. Line 17. PDHD with line search. Prox G conjugate. Prox conjugate. Prox. Okay. You're joking. Too many input arguments. What is Prox G here? Prox G SPIRiT reg H has too many input arguments. Yeah, okay. It's an indicator function, so we don't use this, so we suppress this warning on this line. Okay. And we're running. That does not look any better. All of that work. And that doesn't look any better. But I have a question. So that was a rather large support. What does the second support look like? That seems to be a much better support, doesn't it? I would say so. What happens if we run now? The second support. This, of course, is just using this hacky noise bound that I created. Maybe that's the issue. I think we satisfied our first goal for this morning, which was to get SPIRiT regularization implemented in this new code. And 2 is not a function, a shared variable. Oh, we were using the shoot. Okay. Okay, now we're using this better support. And I'm hoping that this does a good job. And if it doesn't, I'm going to blame the noise bound and then fix that. And then if that doesn't work, then I will panic. But not until then. But I will panic. This PD30 sounds interesting to me. Is there a significant difference between these two? No, there is no noticeable difference between these two. Okay. Just to be sure, yep, I'm definitely showing the new one. Okay, SPIRiT Reg GAM and SPIRiT Reg GAM 2 have no noticeable difference. I'm quite surprised by that because one has a better support than the other. I think we are undersampling by 6, which is, not a trivial amount, and maybe this is what that does. Okay. This is using PDHG when I haven't supplied noise bound or anything. SPIRiT Reg now only takes, what? Oh, it should have been SPIRiT Reg new. Whoa, see, broken. Why is that broken? Can you tell me that? Image 0 is undefined. If we decide to warm start later, we can do it here, and this should still work. Okay. That's what model-based reconstruction does. I guess I'll call it MFS. Now let's call this MFS PT. We'll pass in a support. Error caused by reshape. What is this line 80 in this line? This says LSQR, error uses LSQR, error in Spirit Reg 2 at LSQR. What is 180? Oh, I see, within LSQR. Reshape. Okay. Mm-hmm. Okay, so we've got a significant noise bound, and that eliminates much of the noise outside the support. Basically eliminates all of it. Cleans things up nicely. So the support is helping dramatically. That is nice to see. Now, what if we just supply? How do I tell it to do Spirit Reg? I give it a W size. That's right. Okay, so what if I now just supply a W size? I'll call it with gamma. So now this should do model-based reconstruction with spirit regularization and not using the support. And we're going to just see index exceeds a rate balance. You notice every time we try something new, it's broken. Like nothing's working until we test it. SACR is not supplied. Okay. Let's add that check. If numL W size is greater than 0 and numL SACR is equal to 0, error must supply SACR if you supply W size. So now this should crash. With this error message, must supply, good. Instead of going backwards, I'm going to put the one I'm testing most recently at the top. So that, I'll test this one first and then the rest. Oh. Too many input arguments, no transpose. Wow, tough, 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 tough. Oh, I see. Apply A is what? A is what? Apply MIFS. WMI. What is A? Apply WMIFS. I see. It's undefined? Okay. Doesn't exist. Failed. Confused how it ran at all, actually. Now it doesn't run. In has shape 256 by 256, so out has shape SK data, right? In has shape SK data. That also has shape SK data. Ooh, how does that happen? That's size 256 by 256. How is that 256 by 256 by 8 during the adjoint? That doesn't make sense, does it? Oh. Wait. WFS minus I, its adjoint is FS transpose, well, here it's FS transpose times W transpose minus I. Yeah, okay. I went nuts for a second. Why does that have size 256 by 256 by 8 when applying the adjoint? I mean, that must have size 256 by 256 by 8. In fact, I'm thoroughly confused now. N has size 256 by 256 but this has size 256 by 256 by 8. Because it's actually this. That was a significant bug in this code. How was it working before? I see, we just sent fs in. Okay, now WMIFS is passing. Now we could call this W minus IFS. Let's make sure that check still passes after I made the change to the code. Yep, that still passes. Okay. You're kidding. Too many input arguments still. That kind of hurts my feelings. This accepts. Where am I? 422. Okay. We're making a function handle for this thing somewhere. Huh? Arrays have incompatible sizes. What's proxf? Prox G spirit reg. Prox G spirit reg. Why did I do that? We're running again. The objective value is totally wrong. I think we're here. Yeah. What on earth is this minimizing? I think we need, yeah, this is wrong. At in GDC in from 1 to NDC plus G spirit reg. One and 1 and 2 and 2 and 3. N in support H. I want to make N in support. Why do we have H there? Okay. Plus NTC plus N in spirit reg. It should be N in DC. N in DC. And 1 in 1 plus 1, 2, and 2. And this we need ADC WMIFS. Pretty tough, pretty tough, pretty tough, pretty tough. Okay, we're gonna have the same issue here. The difference is that we're not calling, we're not doing the identity matrix in the middle. Okay. Let's take away the I there. I mean the little w. Now, let's see how that works out. Taxes are coming, everybody, in the US. Don't forget to file taxes, the most joyful time of the year. If they did it during the holidays, everyone would freak out and taxes would end right away. Okay, there's a bug and it's going to be tough to find. Now, I used to vectorize this on the output. Is that the issue here? X is empty. Okay. Why is X empty? N1 is 89368. What is this? N in spirit reg. What is N2? Oh. Oh. I hope that's the issue. Yeah, okay. Dimensions of arrays being concatenated are inconsistent, which is why I vectorized that at the output. But if I vectorize that at the output, G spirit reg H. Where is G spirit reg? What? Out is 0? Oh, I see. Prox G spirit reg. Okay, so now out, I'm vectorizing it. Yeah, now everything runs. The only issue is it only runs now, right? I think it's going to crash here. Or here. Never mind, everything just works, okay? Then why did I take away that vectorization? Was I just trying to be efficient? More spammers on Twitch. Okay. So it seems like we have running model-based reconstruction with spirit regularization, and that's it. So we have just regular model-based reconstruction with a non-zero support, model-based reconstruction but without a noise bound, model-based reconstruction with just spirit regularization, what am I going to call this? Support noise. This one uses Vista. It's clearly so much faster. Okay. This is going to be the support with spirit regularization, but without a noise bound. Okay, found another bug. So here we're doing spirit regularization with insisting that everything outside the support is 0. I don't even make it that far. where does end support get set? We're going to have to add a PT here. The way I've created this now, I mean, I have to make a transformation that is apply A. What did I think was going to be apply A? So G spirit reg is greater than 0, but G support should not be. Yeah, if numL way up. Yep. Oh, no. Thank goodness for undo. ADC changes automatically. Why did that fail? All right, gonna have to think. Gonna actually have to actually think. Okay. ADC is MFS, what comes in is something of size image. But what if ADC is MFS PT? What I just did works. Okay. FS now is always FS PT when it needs to be. Big change. Okay. So we don't need to apply ADC anymore. Where's P? Right there. Okay. Let's create P. Let's create MFS. Let's create P before FS now. Because FS uses it, right? Is in out support used anywhere else? Yes. But just when the noise bound is supplied. Okay, so we'll do these things right before G support and G support H. This seems like the right place to do it. Let's see what crashes. I've lost where I was. Let's see if anything works now. Nope. Fails. P, S, F. F, adjoint, S, adjoint, P. So this is PT actually, so P. Oh. Okay, at least one check passes. So this should actually just be S image 0. Now wherever there's S image, you could just do S image 0. Maybe not for this one. There is no MFSPT. All right, let's see what crashes. All these other things use P, so we should probably check P first. We would only check it if the support's greater than 0 and the noise bound's equal to 0. All right, see if this crashes. That passes. That passes. Ooh! That one crashed. This image 0. Okay. Moving on. Ooh. The last check fails. MFSWMIFS. MFSI. I gotta do that. Okay. SIWMIFS. Oh. And then FS has P in it, right? Yes. Okay. But then what is out here? G support H. Yeah. And NDC is NB. Great. So it's like this G is the L2 norm, maybe 1/2 the L2 norm squared. if support is supplied but not a noise bound, then and a noise bound, then this constraint is added. Okay. The data consistency term is by default is if a support is supplied but not a noise bound, then ADC is equal to MFSPT. The objective function is the problem to solve without any other parameters is that. Where this now is ADC. Okay. If a W size is supplied, then the problem is also constrained by n is the number of and gamma is a scalar or a vector. What? Or by default, gamma is determined automatically as a vector. One value per coil. Constrained by Okay, what on earth is happening now? I just want to make sure it's MFSIWMIFS and not MFSFSWMIFS. If this is really what it is, then this is correct. Two and a half hours already. I have no idea. Okay, for this problem, so here we're doing spirit regularization and support. And this definitely does do ADC. Okay. SHFHMT in is equal to apply. So MT in is equal to apply M in transp. WMIFS. So it would be S. Okay, no. WHMI is equal to apply WMI in up. But here we're going to do from 1 to N1. Here we're going to do N1 plus 1 to N2. No. Two plus N1 plus N2 plus 1 to N2 plus N3. Okay. And 1 is going to equal the output of MNK data. And 2 is going to equal NB. And N3 is going to equal NK data plus NB. And 3 is going to equal NK data plus NB plus WMIF NK data. We're going to call this a concat. This is going to be reshape SK data, reshape sk data, and then into I in is going to equal, so this should maybe be like in 1, in 2, in 3. Reshape in from n1 plus 1 to n2 sk data. Out is equal to apply fs mtn1 plus in2 plus whmi in 3. Concat. Okay. Let's see if that passes. Now we're not double doing fs. But it doesn't pass. Apply M. MB plus, all right, what is M2? I think it's N support. I don't know what I was thinking just a second ago. I guess it can't be. Right, okay. So what is the output of in here? Four six six one four. In support 46614. The I does not multiply fs. I keep forgetting what function I'm minimizing. G is data consistency plus G support H. What is G support H? I guess this is when this is when it's the size of the image. Okay. So then this is an image. So out here is fs in MFSN in WMIFS in, which is equal to, well, so what is its adjoint? MFS transpose in 1 plus in 2 plus FS transpose WMI transpose in 3. Out of curiosity, I don't want to do that. Okay, going back, going back. Okay. Here in is the size of the image. So I could rewrite this like this. Then I could take this, put it there, and then I could distribute the FS. That's what I'm trying to do here. So MT in 1 plus WMI H in 3 . Now the thing is, that should output, everything should output something of size image, right? That's what I'm confused about. Because this is going to be size S image. Let's see if we could get to there. Number of elements must not change. I do not understand. Okay, I was wrong. This outputs something of SK data, and this also outputs something of SK data. It's when we take the adjoint with FS that we get something of size N image, a size S image. So let's reshape that. I don't know that we need to reshape that, plus I into. Okay, we'll just call that into. Now I think that's going to work. That is indeed the size of, oh, this should be S image. Why? Why did that crash? Must not exceed the number of elements. Okay, this is going to be an image, NB plus an image. What is N3? So N1 is NK data. Nope, nope, nope. N1 is 89368. And B is 89368. Great. This is 256 by 256 by 8. Wait, N is size 46614, not the size of N image, size of N support. 46614, which if we supply a noise bound, okay, that was the issue. Why? Okay. Index exceeds the number of array elements. N3 is 660270 and N is 660270. That's why. Oh, come on. Incompatible sizes for this operation. Where am I subtracting? I need to reshape. Okay. Size into, okay. It passes. Wouldn't you know it, it passes. Okay, apply MFS. There was a supply V MFS, which we use there. So now we don't need this. I think it's a good thing that we put P inside the FS operation. Is there a FSPT? No, it's nowhere. Okay. Vectorized version of apply MFS. Still crashing. Where does that get used? See, this is concatenating, and I think this is also concatenating, right? So we're going to say concat. Okay. This is this without the I in the middle. Now we only call fs once, which is more efficient than what we had before. Got rid of that to-do item, which is the best part. And see what crashes now. Still not functioning. Eight nine three six eight, 89368, NK data, NK data. Does that crash? No. So of course, and 1 plus 1. Okay. We're iterating. It's a pretty tough code to write when you have a whole bunch of like options in a code like this. You have to test each combination of inputs. There's a book called Clean Code about Agile programming, and they suggest not doing that. Don't have binary flags as inputs. Okay, but then you have to make just as many functions to accommodate all the combinations. I don't see the benefit one way or the other. So I do it this way. That's working. I have two SPIRiT regs, MFSPT. What's the difference between these? This is with GAM. All right. So we know that this one runs. Maybe I should call this like, yeah, let's just call it that. So this is doing the support with a zero noise bound and SPIRiT regularization. This is just doing SPIRiT regularization. This is just doing the support with a zero noise bound. This is just doing data consistency. Does it make sense to do? Okay, that we've seen already. Now we're doing just the spirit regularization without the support. Now, what I was going to ask a second ago is, does it make sense to do spirit regularization with the noise bound? The answer is yes, but we don't have that implemented yet. And that's, a whole other can of worms. So let's not worry about that. Okay. Those two look similar. The spirit regularization does not look as good as the spirit regularization with the non-zero support. The support is helping. Okay. What was that? That was, yeah, okay. Now we're just using the support without the spirit regularization. And now we're just going to do model-based reconstruction. Which is that. Okay. Things are working. Have we already, so the noise bound, what is that about? That's with the support, right? That's, okay. So first things first. Now let's do the noise bound. MFS, no, NB. MFS, NB. I'm not really checking to see if the results look good here. Just seeing if it runs. So this is just the support with the noise bound. We're using Vista. That's cool. The code automatically chooses, the optimization algorithm that's most efficient for whatever problem it's selecting, which sounds sophisticated, but turns out to be just an if statement. Either way, I'm pleased. Okay. Now, we're going to do spirit regularization with the support with the noise bound. This goes back to, shoot. This goes back, so now MFS NB GAM. Ooh, it crashes. Why did that crash? Reshape. Oh, come on. Come on, come on, come on. Okay, it's in the check. It's in the check. What is S image 0 here? 256 by 256. Wait. This should only be done if the support is greater than 0. Or does it matter? Should it run either way? Because that's running, right? So it's got an adjoint. And support. That support only gets used. No, I actually need it. Okay. Okay, so that's the issue. If numL image 0 is not equal to n image, then that else end Oh, hold up. Do we have an n image 0? No. Do we have an s image 0? N image 0 is equal to numL image 0. And support n image 0. Because n image 0 changes based on whether or not we're doing PT or not. Passes. Does it run? No. Index exceeds the number of array elements. $379. I think it's the same thing. I think this is getting n image 0. But wait. Why are we doing that? How did we get here? We're using GSpirit reg, but G support H. Is that what I'm intending to do the support with the ACR? Oh, okay. Forgot what I was doing. Then what is G? G support H. I want to set a breakpoint here. What is n image 0? What is n2? 154904. And 54904. Oh. I need to know what n2 minus n1 is. $65536. Fine. G support H. Where is G support? do that? N in support. And in support should now be ML image 0. Right, so where do we have N image 0? N image 0. N image 0. Okay. X is 65536. Okay. So is it G Spirit Reg that's failing? Oh! How was that working? Maybe we didn't do it before. I don't know. Okay. Still crashing. That should just be N3. There we go. I'm thinking about when we go to compressed sensing next. And my fear is it's going to start to add in wavelet artifacts in here. Like this will look about the same, but it'll just start adding in wavelet artifacts here. I don't like that. Of course not. That's an image. And I think that's with all the tricks we've got so far, right? That's with the non-rectangular support and the non-rectangular field of view and with the noise bound. Now, so now what? We've added in SPIRiT regularization. I wanted to do two things today. One was add in SPIRiT regularization. The other was set the noise bound automatically. This code is replacing this code. We're getting rid of that. This gets replaced with, all right, so we've replaced our old code with the rewrite. And we don't need this anymore. Load data. Okay. Do we have noise chords? So the right way to figure out the noise, the bound on the noise, is to image on the MRI machine without any excitation and then look at the statistics of the result. This is analogous to taking a picture with an optical camera with a lens cap on or in a perfectly dark room. All you'll see is like the electronic noise. With MRI, all you see is the thermal noise. Min X, min Y, max X, max Y. Looks like we got it. Okay, so I'm using Variable sample mask not found. Shoot. We're in data case 9. So we're not at the MRI machine, and the data's been collected and saved long ago, and we didn't, for whatever reason, we don't have an excitation without any, an acquisition without any excitation. So what do? Well, we're going to look at a part of the image that doesn't have any sample, a part outside the support. So here's K data. Let's recon the true. Okay, this is the true recon. Noise chords are what? 10, 10, 80, 80. What? That'll be like over here, which I guess works, but look at all of this over here. Size image true. 256 by 256. This is data case 9. Load data case 9. Noise chords, okay. Noise chords is equal to, min x will be what? What's 256 divided by 3, divided by 4 times 3, 192. 192, 192, 255, 255. Okay. Oh, shoot. No. I want 256 divided by 4 is 64. So in y, I want 0 to 64. So noise chords is min x, min y, max x, max y. So in y, I want 1 to 64, I guess. All right, so let's get the noise bound here. So noise values is equal to, IFFT recons is equal to that. Noise values equal IFT recons. Noise chords 2 to noise chords 4, noise chords 1 to noise chords 3, and then like that. Noise values 64 by 64 by 8. Okay. We'll do the simplest thing first. So the noise bound is equal to the norm noise values squared, the L2 norm, divided by the number L noise values. But that's across cross coils. So the simplest thing is to not do that. Instead, to take image true, not worry about the multiple coils. Okay. Let's see what value of noise bound we get. 4 times 10 to the negative 8, which is much higher than the 1 times 10 to the negative 12 that I've been using. That kind of bums me out. The noise bound comes into play with the support. So for all these things, it could be if num_l, if n image 0 is not equal to n image. I guess in this case, it's wait. Okay. If n image 0 is not equal to n image, comes into play there. Value squared divided by the number of the outer support. This is where it is. It's in the g of the, it's in the indicator function for the support. So the norm of the data, am I doing, yeah, I did the noise values colon. Okay, so the norm squared of the data by the number divided by the number outside the support should be within the noise bound. That's what I'm saying here. And when I do that, I think things are about to get a lot noisier. Or just not work at all. And out support. Okay. Yeah. Well, maybe not. I don't know. It's noisy. It's noisier. It's noisier. What happens if we don't supply? So what is this? This is just the support. that was with the support with the noise bound. So you see it's not doing any better than just model-based reconstruction. Okay, this is with 0 outside the support, and that looks amazing. I mean, that looks really good. It's noisier, I grant you, but it looks really good. The average value of the norm squared. So there are a couple of things that are going on here. Like we took into account gamma for each coil, we can do that with the noise bound. So we've now set the noise bound automatically. Let's add a new to-do item and take a different noise bound into account for each coil. And that would be, a reasonable thing to do. It is possible that this bound is just bad. Like, am I thinking about this totally wrong? Does it make sense to take the average value of the norm squared? Here I'm taking the value of the L2 norm squared, the Frobenius norm squared, and dividing by the number of elements in the outer support. So this doesn't look terrible to me. Okay, so we could do this one noise bound for each coil. Oh my gosh. The sample mask is terrible, I think. Oh no. I just don't need it anymore because I make it here every time. Let's fix that. Wait. Okay. It doesn't matter. We're going to be doing compressed sensing soon, and that'll change what I just said, so let's just leave it how it is. All right. The other thing is this bound that is an L2 norm bound, like this is an indicator of an L2 norm. Well, conceivably, I mean, this wouldn't happen, but conceivably it could take all the energy and put it into 1 pixel outside the support and set all the other values outside the support to 0. That would still satisfy this indicator function. The result would be 0. But the probability of that happening when we know that the noise is Gaussian noise is infinitesimally small. So I've always thought that maybe using the L2 norm here is not the right thing to do, and we should instead have an L infinity norm, or have one indicator function for the L2 norm and a separate indicator function for the L infinity norm. I think that's the right thing to do. Because we know it's Gaussian noise, so we know the probability of being like, 3 times away from the standard deviation is very tiny. Well, we accomplished the goals that we wanted to do today. We've been going for 3 hours and 40 minutes. I'm going to call that complete. And we'll see when we do this again. Making progress, making progress. We'll see you guys later.